Hello and welcome to our April 2025 Bite-Sized Corrosion series, where we are spotlighting some corrosion failures. During our current series, we've been breaking down corrosion failures into interesting, informative, and palatable nuggets of information. And we've spent some time looking at what happens, why does it happen, how does it happen, and what could we do to prevent similar failures in the future. So if you've just encountered your very first corrosion failure, or if this is a topic you know quite a lot about, I'm sure you're going to find some valuable insights during today's discussion. Because joining me today is Deon Slabbert. Now, Deon is a well-seasoned metallurgist who has many years of general experience and more recently has moved back to the coalface, as it were, and he's working with Shell and Moerdijk in the Netherlands. So thank you so much for joining us today, Deon. Now, Deon, working in the petrochemical industry, I know it means high temperatures, probably some complex chemistry, materials that need to be star performers under extreme conditions. But as we've explored in this series, I think it might be helpful to see if we can understand if there's any way that we can anticipate corrosion failures before they happen and kind of stop generating more content for discussions like today's. So is there something we could do to kind of preempt a failure?
Yes, Vanessa, indeed, dealing with high temperatures and high pressures where the substances are often flammable, toxic, or even lethal, it's obviously critical to keep those things inside the pipes and inside the vessels, really. And that is the job of the corrosion engineer, is to ensure that those things are managed well and that they don't escape. And it's also a requirement of legislation that one needs to comply to certain rules to ensure that the plant is operated safely for the people as well as for the environment. So typically, part of that, you need to inspect plant on frequent intervals. That is legislated, typically every 3 years. Right. But you can extend that if you've got a system in place. And one does that with a process or a system that we refer to as a risk-based inspections, or RBIs, as most people would know it. So risk-based inspection is really the system that manage, and most plants use RBIs to manage the plant to a large degree, where you, on the one axis, you determine what is the probability of failure. So with that is where the materials and corrosion engineer plays a big role, is to identify in a specific process, in a specific combination of corrosive species, temperatures, pressures, contaminants, everything that is there, coupled with the materials that is there, you identify then what are the likely damage mechanisms that you can expect. And then you then assign a likelihood factor to that, to say, what is the likelihood, what's the probability of failure in that specific system. So that's typically on the one axis. And then on the other axis, you determine what's the consequence of failure. And typically there are then three things that you consider there. One is then safety, basically how many people are you going to kill if there's an accident, failure.
Hopefully none, yeah.
And then the second item is then, what's the cost going to be of this failure, so the monetary impact thereof. And then the third one is then the effect on the environment. So those three things you then plot on the x-axis, and then typically on the y-axis is then the probability of failure. And then you get a matrix, and then from this matrix you can then get a criticality rating, where you can see what is high risk and what's medium risk and what's low risk. And really you manage your whole plant really based on this. You assign then also confidence intervals based on this. This then is then used also to determine your whole inspection program. What do we expect to see? So is it general thinning, or is it cracking, or is it pitting? So that will determine what methods you would use to inspect. And then you also then use that to see, where should I inspect? Where do I expect the damage to occur? And then also how often. So what method must I use? Where must I go and look for it? And how often must I go and look for it? So, and all of this informs part of your RBI program and feeds into your RBI system. This RBI system is also then rolled out to so everything that happens to the plant. So typically the plant is OWAPs, or, operate within allowable parameters, or integrity operating windows, IOWs, are typically also used. So from a corrosion perspective, you then decide what are the parameters that the plant can operate at. And whenever these parameters are exceeded, whether it's a pH level or a temperature or a pressure, all of these things are then fed into this RBI program. program, so that when you look at it, the system, you've got the full record and the history of the equipment. And this is then also fed into, so when you do have a turnaround or shutdown, you can then consider what has happened to the equipment and if there were exceedance of things, or if things have been repaired or replaced, or maybe a new damage mechanism that you didn't anticipate has been found. All of these are then fed into this system or this RBI program, which then helps you to plan for your next shutdown. And if we then have seen some exceedance and we expect something have to be replaced, then before the shutdown, you can then already order spares for things, or schedule other inspections, or extend inspections to other places where you wouldn't have necessarily done inspections. So all of this is really done. And a lot of it is really to do with saving money. If you do it by this, then you can then extend your inspection intervals. I mean, obviously it costs a lot of money to turn off the plant, not to have any production, and to have a lot of people there to build scaffolds and to open the equipment, to clean all of the equipment. So if you can extend that timelines, that's obviously important. But then when you go through the trouble of spending all that money, you want to make sure that you look for the right things, using the right methods at the right places to detect the damage.
Yes, I would imagine that this is quite a useful tool to kind of direct you to looking for problems where you expect them to happen. And I'm sure some things get missed, and I'm sure that it's very dependent on the data that you feed it. So if people are not, if I can use the term, being honest, when there are parameters that are exceeded or changed or whatever, those can negatively influence the outcome. But I know in other industries, this kind of concept has certainly helped to reduce costing associated with inspection, because it's been proven that you can reduce the inspection intervals and just look at what is critical. Now, sometimes people do change processes, and what happens when they do? Can that cause any problems from a failure point of view? I mean, would you anticipate that in your RBI maybe?
Yeah, so obviously your RBI, you assume certain parameters, certain conditions, and we know corrosion, small changes can have quite a significant impact on the corrosion. You can introduce a new mechanism that you didn't have before, or you can change the severity or the rating of that, how fast it happens. So we all know about chlorides in stainless steels, the effect thereof. But there are also other things that can have a good impact, for instance, oxidizing species and reducing acid. For instance, stainless steel. We know typically that you can't use titanium in sulfuric acid, but the titanium corrodes, and then the titanium ions that form there, those oxidizing ions then help to passivate the titanium, and then you can use it. And the same for stainless steels as well, where if you've got ferric ions in sulfuric acid, you significantly extend the useful life or useful area of a specific type of stainless steel for different concentrations and temperatures. So it goes both ways.
Yes.
But you need to understand that. And certainly when you do make changes, you need to manage that well. And we refer to that as the MOC process, the management of change. So whenever you want to make changes to the process, then obviously you've got your reasons to make those changes, but you need to consider what would be the impact on the materials down the line. One specific interesting case where that was not done very well was in a reformer furnace, where in the catalyst, to prevent coking of the catalyst, carbon formation, there was an additive that was added. The process engineers decided to change this additive to another type. I can't remember if it was a cost-related drive or what the main or more effective, but they made a change to the process. They changed the additive to the catalyst. And then so a few months down the line, the heat exchanger downline that cooled the reformed gas that came from the reformer, that cracks. This is quite a large piece of equipment, a big heat exchanger. And then so in between the two heat exchangers and where the gas is cooled, they had cracking. And this was also just maybe interesting, also just, having good relationships with different people. Our corrosion engineers don't know everything. So
Sure.
it's good to have good relationship with like the inspectors on the plant. But so what was interesting is what the maintenance guy one Monday morning came to me and said, there's funny mushrooms that grow on the equipment. So there's those little white spots there in between the welds. So that was the little mushrooms that they said grew. So if he scrapes that mushroom off, it grew again. And he wasn't sure what this was. These are large, heavy stainless steel flanges. And when I went there to look at it, I could clearly see now there was definitely a problem, and that these things were perforated and came from the inside. And it was all the way around these flanges. And shutting down the plant is obviously huge, with millions of pounds lost in a daily. So it's not done recently, but I can always remember the feeling I had driving back to my office from the plant, because I knew this was a serious integrity and safety threat, and this thing could blow up any moment. And I driving back to the plant, and you can only drive 30 kilometers an hour, but to my office, and I immediately contacted the manager and said, you need to shut down the plant now.
That's quite a decision to take, hey?
Once we opened it up, you could see when you look down the flange all the way around, so when we did the dye penetrant test, the red marks are then where the cracks are. So there are cracks that was right around the flange. And then the next picture, if I micrograph, so you can see the weld is in the bottom, and the whole structure is just crisscrossed with cracks. So that thing was fraught.
Well done for saving lives.
And that, as I said, that was 60% hydrogen, high pressure, high temperature. Yeah, so that was quite a concern. And so the investigation then actually revealed that was 304 stainless steel, and fell due to caustic stress corrosion cracking. Interesting, stainless steel doesn't have much better resistance to caustic carbon steel. If you look at the NACE caustic curve, it goes directly from carbon steel to post-weld heat treat the carbon steel. If you've got higher, more severe conditions, higher temperature or high concentration, then it goes directly into nickel-based alloys. So stainless steels is not much better than carbon steels. And so in any case, after a long investigation and trying to find out what happened, we discovered that the additive that the process engineers changed to add caustic in that. During process upset conditions, that volatilized, and this location was then basically at the dew point where the caustic then reformed and basically condensed out and at that vessel.
The other thing that story demonstrates to me is the value of just the routine, open-eyed inspectoral maintenance and just doing his job, but not just internalizing everything, but actually taking the initiative and saying, this doesn't look right.
Yeah,
Deon, that is so interesting when we don't follow the change process, and you were able to identify what caused the problem. But I think sometimes also it's easy to finger point and to blame one either set of environmental conditions or contaminants or whatever for causing a problem. And sometimes that's not always the case. And you mentioned that you were involved in a scenario where that was pretty much what happened.
Yeah, one of the interesting and was one of the more challenging investigations was where the plant was built in 1979, and then I think when we went through the records, the first failure of heat exchanger tubes occurred in 1982. So it was like three years later. And since then, it was at that stage it was brass, copper-based tubes that was used in that. And various reasons were given over the years for that. Yeah, and I only got involved very much later on in the system. But obviously the water, so it was water that flows through the tubes on the inside, and that then condenses the gas on the outside. And obviously it failed due to putting corrosion on the tubes from the internal side, and the water is in contact with that. So it must be the water's fault. And the poor water treatment company were always in high jump and had to explain different inhibitors and things were used. But they could never solve it. They even changed from brass to copper nickel based. I don't know, it's still copper based, but copper nickel. And copper nickel tubes are used for condensers, even in for seawater. And this is only it comes from potable river water, very low salinity, 50 ppm of chloride versus 18,000 ppm in seawater. So to identify what the cause for that was a challenge. But what does help is to have a good management system and a good structure, and people that back you, to do tests, and so we could actually do laboratory tests, and we also then, based on that, we had a good idea of what it could be. But to confirm our hypothesis, we devised test rigs, which was then based on, I don't know if people know the old Dutch system, the deposit accumulation test station where a heating block is around the tube, and then the material flows inside because it's a heat exchanger. And to simulate conditions accurately, you needed the heat exchange part of it. So we made 6 of these rigs, and we tested different materials, different flow rates, and different conditions. And so basically from that we could then show that the damage was actually not due to the water itself, but was due to hot spot corrosion, which is basically where you get a thermogalvanic cell created based on temperature difference, the temperature gradient, and that creates a corrosion cell, and you get corrosion based on the temperature difference. There are obviously things that makes it worse. So too low flow rate, then you get higher heat. When you do get scaling, then that local area, the heat is then different, than from where you don't have scaling. So minor differences in that does have an impact. And also the water, but you can get this pitting even with irrespective of the water. If you do have some species in it, does make it worse. So for instance, ammonia, even 2 ppm of ammonia will make it worse. And also sulfides. And when you've got ammonia and sulfides together, then they act synergistically. Then you need less of each to cause the corrosion. So that was quite interesting. But I think the main thing is to identify what is the root cause. And once you understand the root cause, then you can make appropriate changes to further damage in future.
That's really interesting, Deon. You actually gave us some lovely photographs which we haven't shown. And I always love the coloration. And here, just the variation in color is also indicative to me now, with the knowledge that you've shared, also of the thermal gradient and the changes.
Again, these are this is 9010 copper nickel tubes with the pitting there. And what was quite interesting, what was quite nice, if you take some of that corrosion product and you look at it under the SEM, then you see pure calcium chloride crystals. The crystals is
wow.
I know the SEM always makes very pretty pictures.
Yes.
That was quite nice. And also the other thing that's also maybe misleading, and a lot of the people that did failure investigations described it as the mechanism as de-alloying or denickelfication specific as the mechanism. But so, okay, how do you fix it? How do you solve it? And so the way I see it is just that yes, denickelfication do occur, and basically you get copper that plates out again, but that's not really the mechanism. The mechanism really is the difference in temperature and the hot spots that's created.
Fascinating. Wow. It's really interesting to consider. And as you say, I think often water is blamed for, corrosion. You need water to have corrosion, therefore it's the cause. So it is interesting that you were able to find the mechanism just by interrogating the data, the situation, and doing test work and determining that actually we're seeing this irrespective of the material, irrespective of the water. Okay, there's something else at play here. So that's very interesting. We're almost out of time, but I do know that you sent through some interesting pictures of some flue gas tubes. So I don't know if you'd like to quickly chat through some.
Yeah, that was also an example where the water was also blamed. That is, it's also a heat exchanger where flue gas is cooled, and then so that heat is then recovered by then heating boiler feed water, which then goes to a steam drum. So this is the bottom side of tubes of the bank heat exchanger, and you can see. Unfortunately, the picture is not that clear, I think, but there's water running all the way down. Here. And these actually failed every 6 months from the install. It was a new plant that they installed, and every 6 months they had failure. And and when they analyzed the corrosion products, they also found chlorides, and therefore they said it was the chlorides and the water treatment. And there was quite a few stories that was given for the reason for these failures. You can see all of the damages from the inside, and you can see the top side is very thin and the bottom side is very thick.
Yes.
But definitely it is from inside from the water side, and therefore it's the water's fault. But what was quite interesting, that's the amount of sort of corrosion products that was collected at the low flow area. But so in any case, after a long investigation, what we actually did find was that there was insufficient flow in the tubes, and then you get departure from nuclide boiling and then stratification of the steam. So in the top half is then basically only steam, and the bottom half is then water. So the effect thereof then is then that the cooling is not effective on the top, so you get overheating. And secondly, also the caustic that forms then concentrates due to the mechanisms called steam blanketing. So that could be due to the caustic that concentrates, but the reason is too low flow rate and stratification. And what's interesting is even above temperatures above 400 degrees Celsius, you don't need caustic. The steam reacts directly with the metal to form, and you don't form a protective magnetite layer. We then put in baffles so that from between the steam drum and this, that you get force flow in one direction, which meant that we had higher flow rates through the tubes. And once they put in the baffles, they solved the problem. And as far as I know, they never had a failure thereafter, which was 12 years ago.
From every 6 months to 1 in 12 years, that's incredible. Well done.
So that's the problem was in some with design. That's where the design was not appropriate.
But really heartening for you as well, Deon, to look back and say, I did something really beneficial there as part of the team. That's fantastic. Deon, we could actually talk forever. This is so fascinating. I'm finding it really interesting, and I'm sure our audience is too. So thank you so much for sharing some corrosion failures that you've really been a part of, that and you've you've inspired me and given me some hope that actually with sound science, with diligent inspection, with perseverance in trying to determine what the problems are, and certainly a lot of skill in identifying the problems, you can solve them and then prevent them from happening again. So well done, and thank you.
Yeah, look, thanks. And just, it's not me only. Corrosion is very multidisciplinary in nature and very complex nature in terms of, you can't be an expert on everything. So you definitely need a good network of people that is good in stainless steel, people that's good in nickel, people that's good in coatings. And if you've got a cathodic protection problem, you phone Vanessa O'Neill. So you need to have people that you can consult, and you can almost phone a friend or a soundboard of things from the process engineers. Know them, they know the process and what happened and what changed, and with the inspectors, they crawl through the pipes and they see things firsthand and they know what happens where. And just the role of what the Corrosion Institute, for instance, plays is just to facilitate that networking.
Yes.
So that one builds up that network, which allows you then to be able to solve problems. These sound bites that you are doing now, that's educating people, putting people into contact with, and that is really a huge role that you play at solving problems and ensure that plants operate safely in the end of the day.
Well, thank you. And thank you for being part of our network. And thank you to our viewers. And I do hope that you leave today feeling like you've benefited from our discussion, that you've expanded your network, and that you will join us again tomorrow at 1 p.m. when we will wrap up our discussion on corrosion failures with Neil Webb. Thank you all.